morning. So geometry, the last contest. So apparently we have some easy tasks with geometry. You can also have those. So we will start with this easy task, and let's start with task C, 11 circles. So the easiest geometry problem ever. So the story was that we have a big circle, and we would like to put inside of this big circle 11 smaller circles of the same radius. So this is like circle with radius r, and we would like to find 11 circles with the same radius which fit in this circle, and small r should be as big as possible. So we can think about like easier problems. Like if we want to fit 2 circles, then like the optimal solution would look something like this. Okay, so then we can easily conclude that r is just, small r is capital R by 2. Okay, so this is easy case. But if you want to insert 11 circles, then it's quite complicated. But so in the problem statement, you got this image which shows like optimal solution. So you can like use this image to actually try to calculate. And this was the problem from one of the Polish training camps. So one of my friends figured out, okay, so let's give an easy geometry problem, and he made something like this. So he said that so sometimes and we talked a little bit in terms of patterns. Sometimes it's a good idea to try to see something in the solution, like some kind of pattern, and then try to guess what will be the correct solution. And you can guess and try to submit and see whether it's correct or not. So he figured out that maybe some teams would like to guess on this problem. So he prepared this input data. So like so you have like for input you have some R0, which is like 15,396 whatever, and the answer is like 3923, something like this. So if you are good at seeing the patterns, you will see that small r is a square root of big R. So guess what? It shouldn't be a coincidence. Come on, because these numbers are like really crazy. So okay. So write a program. Just calculate the square root of the number on the input, and you get the answer, and you submit, and you hope for accept, and obviously you get the wrong answer, because come on, this couldn't be true. Well, it's because let's say that if r is equal to 1. Yeah, 1. Yeah, 4. Okay, yeah, 1 is also 1 is also a good example. So then you get as the answer 1. But the problem is if r is like smaller than 1, so r is like 1/4. So what is the answer then? Yeah, it's half. So it's like smaller circles are even bigger than the big one. So obviously it's not a good solution. But the input case was designed as to. So there were teams who submitted square root like here, and also in the Polish training camp there also teams who submitted. So in our camp actually there were some teams who worked like really hard on this problem, and they figure out what is based on the image, they figure out what is the formula, like mathematical formula how to calculate this small r. So it's like we was like, whoa, that's nice. But you couldn't do it like in 6 minutes, and there were like solutions to this problem after in unofficial contest after 6 minutes, and official 15 minutes. So it's like there should be something else in this problem, and there is. Actually, the input and the example was crucial here. So if you see what you need to do, you see that the output says that you must be correct up to 6 decimal places. So your absolute error must be smaller than 10 to the minus 6. Okay? And you can see what is the input. The input R is up to 10 to the 6th. Okay? So because you know that the answer will be smaller than the input, okay? Because the smaller circles are smaller than the big one. So you know that also the answer will be smaller than 10 to the 6th. So how many digits you need to have like in the answer? So answer can be like 10 to the 6th, but you also have this absolute error 10 to the 6th. So your relative error must be smaller than 10 to the minus 12. Okay? So you have to output 12 correct digits. But if you see the example, both of these numbers in the example have 12 digits. All right? So actually, well, this is not true, but what is true? So if you think about, like, if you make a big circle 2 times bigger, so what will be what will happen to the smaller circles? They also get 2 times bigger. So obviously, if you have some, like, if you calculate the ratio R to the of big circle to the answer, so this actually you will have the same ratio as in the input sample. So you can calculate that small r is just r times r0 divided by r0. All right? And these numbers, r0 and r0, have enough precision, okay, to calculate the answer up to the 10 to the 12. So we can use the input sample to actually produce this formula. All right? And the time complexity is constant, yeah, because you're just multiplying the r with this number. All right? So the easiest geometry problem ever. All right. Okay, so this was problem C. We can go, yeah, I think problem B will be the next one. So problem B has a very appropriate name, computational geometry. So in this problem, we have some story about Baltazar, who is preparing the hardest task for the contest. It will be the task about computational geometry, but like this task is not very hard. We need to construct a polygon which has the edges parallel to the axis. So the polygon could look like something like this. All right, and the coordinates should be integers, and then one additional requirement is that the number of vertices is equal to the area of the polygon. Okay, and we are given in the input we are given the number of vertices. So we are given some number n, and we must construct a polygon with n vertices, and the area is also n. All right, so, and we got some easy example. So if n is equal to 4, we can just let's draw some grid. So we can construct a square of size 2. All right, so it has 4 vertices, the area is also 4. So one question is, sometimes there will be no possibility in constructing the rectangle, the polygon, and of course, if n is odd, we cannot do this. All right? Well, it's obvious because like every polygon which has sides parallel must have even number of vertices, because like every side is we have alternately horizontal, vertical, horizontal, vertical, horizontal, vertical. So we have even number of sides, so of course even number of vertices. All right, but for any number bigger than 4, which is even, we can construct such polygon. And because this is like the constructive task, so actually we have like much freedom here, and there are like many solutions to this problem. Yeah, so I will show one possible solution. Okay, so we can think about about the next complicated thing. So we have like an example for 4. So what do we do like if we have like 6 vertices? Well, for 6 vertices, I think we can only do something like this. So our polygon must be of this kind of shape. Okay, so here we have 6 vertices. If we make the smallest polygon possible, it will have area of 3. All right, 1, 2, 3. But we can like stretch it a little bit along one axis. So if we like stretch it by factor of 2, so this will be divided, and so we will have 1, 2, 3, 4, 5, 6. So the polygon will have area 6. So the area we are interested in. So actually, this is a good candidate for to start our algorithm. So we can just draw this here. So this is the polygon with 6 vertices and of area 6. Well, so if we would like to, so we would like to construct a family of polygons. So it's so we would like a procedure which shows us. Okay, so let's start with polygon of n vertices, and let's try to add 2 more vertices in such a way that the area also increase by 2. All right. So what can we do here? Well, we can do. We can make this polygon look more symmetric. So we can remove this part, and we can like add additional additional part. So we are adding this part in such a way that we are introducing 2 more vertices, because we are introducing this one and this one. Okay, and we also make sure that this part has size 2. All right. So we can add just something like this. Well, and if we want to add something similar to create a polygon of 10 vertices, we can just like extrude this part. So we can take this right here, we can add something like this. So we'll be introducing this vertex and this vertex, and once again the area which we increased is by 2. All right, and we can do this like indefinite, like forever. Okay, so we started with the polygon of size 6. We added this part. Then we added this part. So then we will add this part, this part, this part, and so on. Okay, so every time we are adding 2 vertices, and the area is increased by 2. All right, and so we can construct like a procedure which will just generate all this vertices, because if we know how this rectangle looks like, we can just like make a formula what will be the positions of of vertices. So basically this algorithm will work in linear time because we have to like output every vertex. Yeah, so we cannot go below linear, but actually if we would like to provide a compressed version of this representation, then probably it will be like even less than linear. Probably you can get like with constant space if you want to compress it. All right. Questions? Okay. Now we can go to the last one, problem I, taxi. Okay, so in this problem we have a plane and we have some points on this plane. Okay, and we are interested in 2 points which the distance between these 2 points is as big as possible. Okay, but the distance is calculated in the Manhattan metric. So suppose that we have like 2 points here and here. So the distance between them is like the difference between their coordinates in x-axis and distance between their coordinates in y-axis. Okay, so if we have like point A and B, so the distance will be xa minus xb plus ya minus yb. All right? So we would like to maximize this distance over all pairs of points. So obviously we can do a n-squared solution. Okay, so we can try every possible pair of points, and in constant time we can calculate the distance between them, and we just output the biggest possible distance. But the number of points is like 40,000. We have like 50 cases, so yeah, so this will be definitely too slow. So what if we want to maximize this sum? All right, so let's put the whole picture in one big rectangle. All right, so if we want to maximize like this horizontal line, so this is essentially the same as minimizing these 2 green lines. All right, so we are like these 2 lines are like complement of this this red line to this green bounding box. And the same thing is with the vertical line. If you would like to have this vertical line as long as possible, then these green lines here should have like the total length of these lines should be minimal. All right. So in principle, the length of all 4 green lines should be as small as possible. All right, but we can draw these lines somewhat differently. So I will take this green line and just draw it here, and take this green line and draw it here. All right. So I didn't change the length of these lines. I'll just draw them somewhere else. Okay. So now our question is, I have this point A, and I would like to minimize the sum of these two distances. So let's suppose that this is like 0.00. Actually, I can like move everything here, so this will be true. Or if the the coordinates are positive, so actually I don't have to do anything. Okay, so what is the length of these two lines?
The sum of the coordinates.
Yeah, so the length of these two greens is xa plus ya. All right? So what if, so let's say that I have to minimize these two. So let's say that here I have like x big and y big, some big coordinates. So actually the sum of these two lines will be, the sum of here will be xm minus xb plus ym minus yb. But xm and ym are constant, so it's basically xm plus ym. So this is some constant, so I will just write it like some constant c minus xb plus yb. All right? So I would like to minimize this number, and I would like to minimize this number. So actually, I would like to maximize xb plus yb. All right? And this is also not, like this is, we can do another picture because we can draw this kind of line and this kind of line. If I want to minimize the sum of the solid green lines, this is the same as minimizing, as maximizing the sum of dashed green lines, and the sum for dashed green lines is xb plus yb. All right? So our question is, I need to find 2 points in such a way that the one point has the sum of the coordinates of one point is as minimal as possible, and sum of coordinates for the second point is as maximal as possible. All right? So I can do just, I can go linearly through all of the points, and I will keep track of the minimal value here and maximal value here. All right? So this will end up with a solution, this will be a linear solution. Okay? All right. So this looks nice, but actually this won't give you accepted because we forget about one case here. So maybe this image was like was convincing enough, but actually we need to be a little bit careful because like in this image we chose the points which were like on this one diagonal. So if when I move this green line, it was obvious that it's better to move this line to point A and this line to point B. But we can have another. But we can have like another picture. So maybe we have some points here, and we have point here. We have point here. All right. And then for this picture, it's obvious that like the optimal solution will be this point and this point. And then actually we would like to minimize not these lines, because this will give a really big answer, but actually we would like to minimize these. Okay? So we also need to consider this case, and in minimizing this, we actually have to do the same algorithm, but instead of taking the sum of coordinates, we'll take the difference of the coordinates. So we will have to find a point which minimizes the difference and the point which maximizes the difference between the coordinates. All right, so we have to consider two cases, the case of sum and the case like the case after like flipping the board with differences. But this case is also in linear time. All right? Okay. Questions? No. What? Yeah. Okay, there's this problem F, problem the invasion. So I will just write down the title of this problem. And I can just say, okay, so this problem was solved during the lecture. All right, we already talked about the optimal solutions for this one. So if you paid attention and if you was not scared about the implementation, then you can get accepted. All right. So what's next? Yeah, well, we have this the first problem with the circles. I think we can do the second problem about the circles. So problem, I believe D, circles and aliens. All right, so we have a plane, and on this plane we have some circles, and they don't intersect. I mean, the insides of the circle don't intersect, but the circles can touch each other. So you can have like something like this, and circles can have different radii. All right. Is this good enough? All right, we can have some kind like this image. All right. And the question is, we need to calculate, we need to calculate the number of this intersection. So the number of points where two circles touch the borders of two circles touch. All right. Okay. So what can we do? Once again, we have like this. We have n circles. And we, like, if we have like xa, ya, xb, yb, and we have also the radii of the circles, so rb, ra. So we can take two circles and we can test whether they whether they have a common point or not. So basically, we have to test whether the distance between these two circles is equal to RR plus RB. All right? So we have to calculate the distance. So in order to calculate distance between these two circles, we use like a formula xy minus xb squared plus yi minus yb squared. So the square root of this must be equal to Ri plus Rb. All right? So we can do for every pair, we can do it for every pair of circles, and then once again we will get the n squared algorithm. One thing which you have to be careful here, it's about two things. One thing is precision. If you want to calculate the square root here, you will have to calculate it using doubles or long doubles, and of course you cannot use this equality. You have to use some epsilon for calculating this. But the thing is that all numbers in the input are integers, so the positions of the centers are integers, and also radii are integers. So it will be nice to calculate everything in integers if it's possible. And here it's possible because we can just get rid of this square root entirely. Okay? And we can just make a square of the right side. And now this formula can be calculated entirely using integers. Okay, so we won't have any precision issues. Yeah, and because we are not calculating like the square root, this code would be faster. All right, but n squared is not. It's very I would say slow. So one thing to notice is how big could the answer be? Okay, why?
Because the best thing you can do is like having the circles in an hexagonal way. So they look like a beehive.
All right. Well, okay. So the answer was okay. So not necessarily we have like n squared, but the max answer would be like 6n, and you gave like the idea of the example that this can be achieved. But the question is why this example is like the worst case. Why can't you achieve more? Okay. So it's like so we have like the lower bound on the maximum value, but we would like to have an upper bound that this is actually the worst case. So one thing we can notice here is that that we can treat this image as a graph. We can treat each point of each common point as the vertex, okay? And we can treat each arc of the circle which connects 2 points as an edge in the graph. All right? So what can we say about this graph? It's planar. All right? So what do we know about planar graphs?
We know Euler formula for planar graph.
Okay.
But give similar to a proportion between number of edge, number of faces, and number of faces in the.
Okay, so we know. So there's a Euler formula for planar graphs. So planar graph is a graph which can be drawn in a plane in such a way that we draw some vertices and we draw edges, and these edges won't intersect. And it's easy to see that even if we draw these edges okay, maybe not the slopes have to be drawn this way, but this is like a correct image for a planar graph. So we have Euler formula to calculate which shows the relation between number of vertices, number of edges, and number of faces. So faces are these regions between the edges. Okay, so for instance, here we have like one face. Here we have like another face. All right? Okay, and so what can we say here about this, this graph? So the number of vertices are the actual number of common points we would like to have. If we look at it, the number of edges is also gonna be, like, we start with n edges. Like if all circles are like disconnected, we start with n edges, and if we try like to connect two circles, we will get another vertex and we will get another common points. But can we calculate the number of faces here? Well, we have a face for every circle, but we can also have a face for like every. Yeah, we can have something like this. All right, so we can also have a face for every like cycle in the circle. Okay, so maybe it's like calculating this number of faces won't give us. It won't be like super easy because we can have like more than faces. All right, so maybe we will not go into detail here. But actually, this Euler formula, which connects these things, we will use it also later. So we'll keep this in mind. All right. So, let's think about the faster algorithm. And actually, using the faster algorithm, we will show that the number of these common points will be much better than n squared. All right. So, what can we use if we have like the bunch of stuff on the plane? What are like the common techniques for the computational geometry? All right. Yeah, we can do some sweeping. We already do for the invasion. We do radial sweeping. When maybe it's time for the normal sweeping with a sweep line. So let's try this idea. So we will be sweeping a line, a vertical line from left to right. Okay, and every time we will be keeping we will have some kind of data structure on this line, and in this data structure we will keep track of every circle which is intersecting this line. All right. So for instance, here on this line, if we have like, so I will write the similar image here. So here we have one circle which intersects this line, and we have a second circle which intersects this line. All right. Okay. So if we have like this sweep line algorithm, we must think of what are the events for this algorithm. So the event, because we need to track which circle is intersecting the line, the event will be, okay, this circle starts intersecting the line, and the circle ends intersecting the line. All right. So when the circle starts intersecting, so it starts when the line is on the like the leftmost point of the circle. So this is actually this point. So if the point has coordinates x, y, this point will have coordinates x minus r, y. All right. So this is like the point I'm starting intersecting this circle. So we can make some event, like this will be event with this point. I'm starting intersecting some. This is circle number I, and I start intersecting it. So this like start. So this will be the event, and the end event is here. So this is like the rightmost point. So we have the point of coordinates x plus r, y, circle I, and this is an event. All right? And so we have all these events. We sort the events along the x coordinate because our data, our sweep line goes along the x coordinate, and then we have to do some work for each event. So the work is kind of simple. So every time we have a start event, we need to put a circle into a data structure. And now is the interesting part. So how the data structure must look like. Well, one important thing is, so let's suppose that two circles intersect, because this is what we're really trying to calculate here. So let's think about, for instance, these two circles. All right, this one and this one. So they have this intersection point here. All right. So that means that if we draw our sweep line through this point, the point of intersection, so what can we say about those two circles?
They are adjacent.
Mm-hmm. Yes. So in our data structure on the sweep line, they will be next to each other. All right? So if on our data structure, if the circles are sorted along the y coordinate, so this is our, okay, so here we have like events sorted by x, and on the data structure, we will have circles intersecting the line sorted by y coordinate. All right? So if we know that if two circles have a common point, then there will be some time during our algorithm that they will be next to each other on the data structure. Okay? So we must test it. Of course, our data structure will not stop at every point, because like the sweep line will stop only at these points. All right? So for instance, if here is the point of intersection, so that it probably won't stop here, but it doesn't matter, because if these circles are intersected, like if they are next to each other in some point, and these events are the only places, like the only places in which we can remove circle or add circle. So actually, we can test during each when we add circle, we can test the neighbors of the circle whether they actually have a common point. So if we have like our line, sweep line, if we have some circles on the sweep line, and now we have the event that I will add some circle here, okay? All right, so maybe I will add circle here. So now, after adding this circle, I can find the previous one circle in the data structure and the next one circle in the data structure, and I can test using this formula whether they actually have a common point. Okay, so this is like I'm adding this circle on y, and this will be like the next circle and the previous circle on the line. So I can just store these circles using a set. Okay, sorted the set sorted by the y coordinates. So basically, I need to store only like the y coordinate of the circle and the number of the circle, the identifier. And then I can use like lower bound or upper bound to find the next element in the set and the previous element in the set, and I have to test whether they have common points. So actually these two will have common point, but if I test the distance between these two, these two have not. All right. So I have to do this for every insertion, but also I have to do this for every deletion of the circle, because I can have such I can have a such example that I will have a circle here. So I have a big circle. I will have another big circle here, and I will have a circle here. Okay. So when my sweep line is over here, all right. So this was like the start event, and this will be the end event for this blue circle, all right. And you can see that the red circles have a common point. So I need to calculate this common point. But the problem is that the sweep line, like on the left side of the sweep line, there was no time in which these two red circles were adjacent in the data structure. Okay, because between them, this blue circle was always between them. All right. So far, we haven't tested y prime and y bis. Okay? So, but now this blue circle will be deleted from the data structure, and now after deletion, y prime and y bis will be adjacent in the data structure. So actually, for the end event, we need to once again find the next element for behind y and the previous element before y, and test whether they are adjacent, they have common point or not. So for the start, we need to test. Y prime and also y and y bis, and for the end event, we need to test y prime and y bis. All right? Okay. So using this algorithm, we will test every possible pair which will appear adjacent to each other on the sweep line. And as we see here, we will that will mean that we will test everything we need. So overall, what is the time complexity? Well, we have to sort the events. We have a linear number of events, so sorting them will be in time n log n. And also, for every event, we need to put something in the set or remove something from the set and use lower bound, upper bound, constant number of times. So basically, the operations on the set will be logarithmic, and we have n events, so there also be n log n. So overall, the time complexity is n log n. That means that actually we cannot have more than n log n common points. All right, because in our program, we just like every time we do the event, we just increase the number of common points by 1 or by 2. Well, actually, we do this for every event, and we have n events. All right. So this shows that even it shows that the number of common points is linear. Okay. So this is really much better than n squared. Okay. So questions? No questions. So actually, this is computational geometry. So usually we have some corner cases. So are there some corner cases that we missed here?
We call count the same pair twice. There is an entering of a circle.
Mm-hmm.
When we remove it, we count it once, and if another circle enters and leaves before these two big ones, the pair will be counted once more again.
Okay, so what will be the example of this?
The same that
This one?
the little one on the right side.
Okay.
The S of the S of this,
Mm-hmm.
the little one, and then you will have
So we would like. So you'd like to put something.
there.
All right. Okay. So what's the problem with here?
When the blue,
Mm-hmm.
green blue circle leave, the two of them are the two red ones,
Okay.
and call the plus one.
So here we will add +1 because we are well here we have +1 because this is like yeah, here we already have +1 for the circles, but when this little circle will like be removed, we will once again test that these two circles are adjacent to each other, and we will add them once more. Okay, so how to prevent this?
We could keep a set of the pairs that we took.
Yeah, so basically instead of like just increasing the counter, we need to track of like on another set, the set of circles which we tested that they have a common point. Okay, that's a good observation. What else have we missed here?
So if you have many circles entering at the same time,
Mhm.
the order the entry. So
Mm.
many circles
Mhm.
starts where the line is.
All right, so we can have okay, let's draw it here. So we can have like this image, right? And we can have like many circles which starts at the same time. Yes? Okay. So the question is, what is the order of the circles?
It doesn't matter.
All right. So one answer is it doesn't matter. Why it doesn't matter?
Because if you put one of them first, then the other will see the one that was before, and the others
Mm-hmm.
intersect with the following.
Yeah, because eventually we will have this situation when we move this line a little bit, we'll end up with this situation when we have these, like there will be in order in the data structure. So actually, because if we keep adding them one by one, it doesn't matter in which order we will do this. So we need to consider one more case. So in this nice image, we showed that like for every intersection point, these two circles must be adjacent on the data structure. But once again, this image was convincing, but this image doesn't contain every possible case we can have with intersection of two circles. And one case we have missed is that these two circles might intersect. Like they can have the same y coordinate, and then they will intersect here. So they will be touching this line. So it depends on how we implement our algorithm, so probably, yeah, so one thing, one important thing is, what if we have, and actually this is the thing about the order. So actually the question about the ordering was also important, but the question about the ordering the end events and the start events, which are happening for the same x coordinate, okay? Because here we will have end event for the circle and the start event for the next circle for the same x coordinate. So the question is how to implement this, and probably we would have thought that, okay, so first we need to consider all the end events, and then we need to consider start events, because otherwise we'll have both these circles on the line, and yeah, and they will like appear in one place, okay? But so either we just say that first we do end first and then we do start, and this is something we need to consider separately. All right? So we can, well, actually we can just consider this as a corner case. So this happens only for circles we have the same y coordinate. So we can just like treat them totally separately. Yeah, so just sort the circles along the y coordinate, and for every circle in the y coordinate, once again sort them by x coordinate and just try whether they are like intersecting or not. But actually, I think if we implement this algorithm with the start event as first and then end event is going, so these two circles, because they have the same y coordinate, they will be adjacent in your data structure. Okay? So actually, this algorithm will work if the start event is before end event. All right, but we need to still need to consider this and be like make sure that we have the ordering correctly. All right, is it 10:30? So I think it's time for a break, if I'm not mistaken. And actually, because we finished this solution, I think we can do this. All right. We do this. So let's think about easier example when we have only one river. So let's think that we have only one river. All right? And we have, let's say, 3 knights. We have knight here, here, and here. So in order to know that this kingdom is protected by knights, we need to find out whether all of the knights are in the same region or there are some knights which are in different regions. All right, so if we have like the line ax plus by plus c equals to 0, how can we know that 2 knights are in the same region?
The cross product of the knights on the line are both positive or both negative.
Yeah, so we learned that the cross we need to find out whether these lines are on the positive side of the line or on the negative side on the line. Yeah, so we learned that we can have we can find a vector on this line, and the cross product then will show us this cross product will show us the direction. All right. So it's if the line is expressed in this formula, it's even easier, because if we plug points x and y here, so we will get 0 for points which lies on the line, and we get positive values for one side and negative values for the other side. But actually, if we think about what is that a and b actually specify the direction, so this will be equivalent to the cross product. But for the line which is expressed in this, you can get even easier. You don't need to find this vector. So we just plug x and y into this formula, and we see whether it's positive or negative. All right? So that means that we can find out for every night on which side of this river he stays. And then we can find out that, okay, we have like 2 positive guys and 1 negative guy, so we have both sides covered. So it's okay. So we have the number of protected regions is 2. All right, so what if we have more rivers? So the thing is, we can do the same. All right, so for instance, if we have like 2 rivers, all right? So with 2 rivers, we have 4 regions, all right? So we have like, for instance, for this region will be like positive on one line and negative on the second line. So this region will have like positive, negative. This will be positive, positive. This will be negative, negative, and negative, positive, right? So for each region, we can write down like this, I would say like an identifier of this region. Okay? So it is like uniquely identified by the sites for every particular river. So we can take every possible, every night and every river and calculate whether this night is on the positive side or negative side of this river. And actually for every night we can also calculate this value, which essentially identifies the region which this night is inside. If we have more lines, so actually if we have like the third line, so this third line will introduce us even more regions, but not necessarily every possible combination will be used. So, but it does not matter. Okay? So like for n rivers, we will have 2 to the power n combinations, but not every combination describes region. But this doesn't matter because we only are interested like in real regions. So for every night we calculate this identifier of the regions, and then we test how many unique identifiers for nights we have. And this is the number of unique identifiers is the number of regions protected by nights. Okay? All right, so what is the time complexity we have here? So for the second part, regions protected by nights, we said that we have, what is the number of nights? So for every night m and for every river, we calculate the site, which is in times m times n. And then we have this kind of yeah, and then we need to compare these elements, but this will be like just binary strings, so you can put it living like in 2 longs or something like that, and we can compare it in constant time. So overall, this part is m times n. And what about the time of calculating the number of regions? Well, if we do the intersection, all of the intersections, we can even do it like in time n square. It would be fine because the number of rivers is 100, so it would be fine. But if we do it this way, then probably we will get even faster algorithm, because then we need to calculate for every, like we need to sort the rivers according to their lines. So for this one, we will get even n log n. But still, the algorithm will be dominated by this. The time complexity will be dominated by this part. All right, questions? So this was like a good example of the geometry problem, which can be solved using a classic machinery. Like applying this standard algorithm will get you the all information, but it's not necessarily like the easiest thing to implement, not necessarily the fastest. But if you observe that if you do this observation, then you can see that you can actually use much more simpler methods to solve this. And usually there are like this geometry problems which appears on the contest tends to be on tends to have this property. But maybe you can use something complicated, but if you observe something, do additional observations, then probably the solution is easier. So if the author of the problem is sensible, then there should be like a easier solution. Yeah, but sometimes there isn't, and then it's not nice. All right, so we did the dragons, computational circles. Okay, so the next one, cross spider. Okay, so this is what was like a 3D geometry problem. What can I erase? Yeah, I think I will erase this one. So in this problem, so this problem E, we have a bunch of points in 3D space, and we are interested whether these points are lying on one plane or not. Okay, so we have points in 3D. Yeah, it will be quite difficult for me to draw a good picture for this. So we are interested whether they are on one line, on one plane or not. And we talked a little bit about this on the lecture, but I'm not sure if I did a good job actually to talk about the 3D version of cross product. So essentially, this is like a standard thing. So so in one of our contests, we figure out, okay, so let's like write the easy geometry problem which tests like the basic notions of cross product. So basically, this is it. So if we have points on the in 3D, so if they're on the plane, in order to test whether they are on the same plane, we would like to find a candidate for the plane. Okay, and you know that the plane is uniquely determined by 3 points that do not lie on the same line. So first, we need to find 3 points which are not on the same line. So one idea is, okay, so let's take point P0, let's take point P1, and now let's, so if we take point P2, it's possible that it's on the same line as P0 and P1. So let's iterate over all different points, and let's find a point. So here we have a line, and let's find some point Pi which does not lie on the same line. Okay? And in order to find whether these points are on the same line, we can use a 3D cross product. So we can test whether P1 minus P0 cross product with Pi minus P0 is equal to 0. All right? If it's 0, that means that all of these all of the 3 points are on the same line. So basically, the vectors P1 and P0. So if you consider cross product of 2 vectors, they are 0 if the vectors are on the same line. So if we cannot find any such point pi. That means that that all of the points are on the same line. So basically, they're also on the same plane. There are infinite many planes, but there is so it's even better. So we answer yes. And of course, we answer yes if there's like less than 3 points. We also answer yes. All right. So what if we find 3 points which are not on the same line? Then we say that they uniquely determine the plane. All right. All right. So we have this plane, and if we calculate the 3D cross product of these two vectors, then the cross product will be a vector which is perpendicular to this plane. Okay? So we have like, here we have the right angle, and here we also have a right angle. All right. And so now we would like to find for every other point pj, so we have like here point pj, whether pj is on the same plane as p0, p1, and pi. Okay? So how can we do this? Well, we can use dot product for this. So we will consider the vector pj p0, and if you remember the dot product was used to calculate the length of the projection on one vector into another vector. Okay, so the dot product will help us to determine this length L here. And so if this length L is 0, that means that the projection is like 0. That means that pj must be inside the plane. So we must find out whether the dot product of pj and this green vector is 0 or not. So if we say that this green vector is like, let's say this is w, so we need to find whether dot product of v and pj minus p0 is equal to 0. All right? And we do this for every point pj. If we have 0 for every point, then we say that every point is on the line, on the plane. Otherwise, we say no. Okay? So, so overall, the time complexity is linear because we need to find pi in linear time, and then we iterate over all pj's in linear time. Okay. So there's so this is like all of them. So there's an interesting story about this task. Because you may be wondering, well, what about the coordinates? What are the coordinates of the of all the points? Because if you're like starting doing multiplications, it's possible that if the coordinates are big, you can go overflow, and your computations are not good. So actually, like for geometry problems, you can have problems with precision if you use like doubles, or if you use ints, you can also have problems with overflow. Usually you don't, but in this, but here we actually do a lot of multiplication. So let's try and figure out whether we have this problem here or not. So what are the coordinates of the integers? So coordinates are from for every point, like x, y, z, will be up to 10 to the 6th from minus 10. Oh, well, minus 10 to the 6th. All right. So we can think about. So what will be the the intermediate values in the cross product. Yeah, so we know that coordinates are about 10 to the 6th. So if we have a dot product, so remember that in dot product, every coordinate is like xa times yb minus ya times xb. All right? So if all of these numbers are like 10 to the 6th, so what will be the magnitude of this number? 10 to the 12. All right. So this is like every coordinate of the cross product. But then you need to make a dot product. So you know that this vector v here, all of the coordinates were like 10 to the 12. For this vector, it will be like 10 to the 6. All right? So overall, the coordinates of this one will be 10 to the 18. All right? What is the amount of is this number will fit in long or not? Yeah, it will fit in long. So long is okay. All right. So you could think, okay, so I'm good here. All right, but actually these calculations were like very imprecise. But the problem is that like 10 to the 18th is actually like close to the precision of the long, right? So what is like the 8 times 8 times or even 9? Oh, okay, so we can say 9. All right. Okay, so let's be a little bit more precise. So we say that coordinates are from minus 10 to the 6 to 10 to the 6. So actually, if we do an subtraction here, what will be the coordinates? 2 times 10 to the 6. All right? So every number here, so this number is 2 times 10 to the 6. So this part is, okay, so this part is 4 times 10 to the 12, and this part, the same. So if I like 8, it could be 8. All right? All right, so this is like 8. So here you have 8 to the power of 12. Okay. Here you have 2. Okay. So overall you have like 16. So is it bigger or? Yeah, it's big. But is it? So so you have 16. Probably if you do something like, or is it like 16? Or did we miss something? So this is like 4. Yeah, but the problem is even bigger because this number here, like for the dot product, you will result in one number, which is like sum of 3 numbers. Okay? So here you even have to multiply by 3. So actually this won't fit, like in the worst case, it won't fit in long. So we didn't know it before the contest. So we choose like 10 to the 6th, you feel, okay, like we did the calculations, it will be fine. All right, so, but it turns out if you like do the precise calculations, you not necessarily have a proof that it will fit in long. I'm not sure if there's really case, if you can construct the case which breaks longs. So there was no such case at least in our test cases because we didn't try to do this. But this is a lesson that sometimes you have to be more precise to actually see what is happening. Because if there's such a case, and if we do some this kind of rough estimations, we'll end up in the algorithm which actually overflows. And this will be a very hard bug to trace. All right, so one question is, what can we do here? Sorry?
Try to normalize the 2 vectors for calculating cross products.
What do you mean by normalize?
Just, I don't know, to divide it by the norm of the
Okay, but still, do you? But we would like to do it with long longs, like with integers.
well, we will need to use doubles.
Okay, so if we use doubles, then we have different problems, because then we need to find an epsilon for our problem. Okay, and then I would say that it's even harder to test whether we are really precise enough for this problem. So where maybe there's some, because like these numbers are pretty big if we want to be precise for long doubles. Okay.
What about if we represent our plane by cardinal instead of vectorial representation?
What do you mean by?
Instead of represent our plane in the vectorial,
Okay.
we can represent it as the cardinal way with x, j, and z.
Uh-huh.
And then replace the points and see if they live in the
Yeah, but so the calculations will be somewhat different, but I'm not sure whether, because we need still to think that in these calculations we are not overflowing. So we will need to see the other, equations, and to see how much precision do we need. So I would like to go with this idea, but try to do calculations in such a way that we won't be overflowing long longs. So there are I know two solutions here. One solution is to use some data type which is even bigger than long long. So usually if your machines judge machines are 64 bits. It's possible that they have some kind of 128-bit type, and you can, if they have it, then you can use it. So usually, on the test session, you can try whether the compiler supports this, and then you know that you can use it. But if you don't have it, and you have long longs, okay. Another thing is that this is only a little bit more than long long. So actually 2 long longs will suffice, or 3 ints will suffice. So we can do big integers using 3 ints. So either you do in Java with big integers, or you can do in C++, calculating the small library for big integers which are not very big. We'll have 3 ints inside. So this is another possibility. And another possibility, which is kind of tricky, is we need to figure out whether this number is 0 or not. So actually, we don't have to calculate this number. We are only interested if it's 0. So if we are interested with when it's 0, we can do a modulo. So we can do all the calculations modulo some kind of prime number p. Okay, and then we can test with high probability whether it's 0 or not, depending on our choice of p. But we can even be more sure. So it's kind of hashing. So we can take one p1. We can take another prime number p. We can take another prime number p3, and then our probability will increase. And actually, if we take 3 prime numbers p1, p2, and p3, each of these numbers is around 10 to the 9th. So this way, our probability will increase to 1, exactly 1. Because the thing is that the product of these probabilities, p1, the product of these 3 numbers is around 10 to 27. All right? And from the Chinese Riemann theorem, because these are primes, so we know that if this equation is 0, if this equation is 0 for all of these primes, So actually, this will be 0 modulo this big number. Okay? So actually, this will be 0 because we know that the answer is below this number. Okay? So thanks to this trick, we can like restrict our calculations to using longs and test whether it's 0 for all of these primes. And if it's 0 for all of these primes, we know that this must be 0. Okay, so this is like a nice trick of hashing for geometry. Okay. Do we have time or do we not? Yeah, we have like 5 minutes. All right, let's try to okay, let's try to do the scissors task. So I think I will do only a hint for this task, but I think it will be enough. So in this task we have a polygon, and we would like to cut this polygon into rectangles using the minimal number of cuts. So for instance, we can like cut this one like this, and then we will partition it into three rectangles. We can have a little more complicated example. For instance, something like this. Then we would, if we want to cut it, so probably this cut will be nice and this cut will be nice. If we would like to have a minimal number of cuttings, we can have even more complicated images, something like that. All right, and so in the problem statement says that we can do, so first we like draw all the cuttings we would like to do, and then we perform them. So actually for this we can draw something like this and something like this, and we can perform it like once, and we have we can partition then this this polygon into rectangles using 4 cuts. Okay, so what is the trick in this problem? So if you think about rectangle is a polygon which does not have any I would say concave vertices. So I draw these red vertices here, so they are concave. Okay, if we are like inside of the polygon, they have like 270 degrees. All right, so we don't want them inside our rectangle. So for every such vertex, we need a cut. Okay, because we need to get rid of this vertex. And actually, if we have a cut for every such vertex, then, well, our cut will not introduce any more such vertices. So actually, if we have a cut for every vertex, we are done. We will partition our polygon into rectangles. So now we need to think, like for every such vertex, what cuts can we do? So for instance, here for this vertex we can do 2 cuts. For this one we can also do 2 cuts. Well, for every here we also can do 2 cuts. So either we do a cut which just goes, which just removes one such vertex, or we can pair the vertices into pairs, and then with a 1 cut we can remove 2 of them. All right. So we would like to have the most number of pairs as possible. All right. So yeah. So the problem will be find every vertex, which is like the bad vertex you would like to eliminate. So we can just go around the polygon and just see whether we are, like here we're turning left, and every time we turn right, we have this wrong vertex. And then for every wrong vertex, we need to find, well, we need to create edge into two directions from this vertex, and we need to find whether we hit a wall or do we hit another vertex. If we hit another vertex, we can create a graph which connects these vertices together. All right? Well, how to find efficiently where these edges go? We can use sweeping. All right? I won't go into details here, but we can do for every direction we can do sweep in order to find where what vertex will this edge intersect. So, for instance, if we would like to find this direction, we can do a line sweep from right to left, and on this line sweep we will be putting our bad vertices. And if we, for instance, here, if we have this line sweep here, we will put that we have this. Okay, maybe not. It's not a good idea. If here we are going downstairs, we can put that here we have some vertex which is still visible, and then we just test on the set whether these are visible or not. Okay, so then we can find a graph which connects all of these vertices, and in this graph we are interested in the maximal matching. All right, because we need to find we'd like to find the maximum number of pairs of vertices which are connected with each other, and then we can have an answer. So actually, there's a funny story. We had this problem. We had the problem before, and one of the teams said, "Okay, so we have to find the matching. We know how to do it using." Because we know that the matching is actually can be calculated by the maximum flow. So they used Dinitz algorithm for calculating this, and they got accepted. Yeah, and later they said, well, actually, because you know the theory about the maximum matching and the minimal cut, and they said that actually it was written in the task statement what have to be done, because the task statement asks you to find the minimal number of cuts. So they said, like, you need to find the minimum cut, so you do maximum flow. So actually, it was all like the algorithm was written in the task statement. But if you look closer at this graph, you will see that actually you don't need any flow, because what will be the structure of this graph? Well, actually, each vertex has a degree at most 2. So basically, this graph is just a bunch of cycles and paths. So calculating the maximum matching in the graph, which has only cycles and paths, is quite an easy task. You have to find how many paths of odd length do you have. But also, the interesting thing is, like, the Dinitz algorithm in this graph will perform very good, because it has there's no many paths. So even though they use Dinitz, they will still have a good complexity, because overall, like, the complexity will be dominated by the fact that you have to do all the sweeping algorithm. So it will be n log n, because then like you have the graph of linear size, and on this graph it's very easy to find the matching. All right, so yeah, I think we have managed to do this in time. Questions, concerns? All right, so thank you very much.